Hello, my name is Gavin Leclerc, and I was the person in charge of designing and developing the Orange Dynamite FRC Team 2583 robot for the 2023 season charged up. And I'm just going to explain to you the walkthrough of the CAD and how we went along the building process. This was a robot we ended up with for competition. The first thing I want to hit were our goals. Our goals were to pick up from one side and have the opportunity to score on the other, be able to pick up both cubes and cones off the ground, and be able to score anywhere on the grid. Those were our four main goals. So now here I can show you. So it was important to us to be able to score on one side and on the other because here I can zoom in. So this was a field right here. And as you can see, there's two line zones, one here and one here, and then the other lines go here and here. And the way this game worked was you would have cubes and cones on this station, and this station, and your alliance was over here, and you were trying to score on these node type things over here, right? So we wanted to be able to pick up from one side because we wanted the robot to start here, come all the way over here, still be in the same orientation, pick up, and then come back over here and score on the other without having to move. That way it just gave our driver a little more like freedom, I guess, is the best way to explain it. So yeah, so that's how we went about the game. And then we also said we wanted to be able to both pick up from the double station and the single station, as we called it, the shoot, because we just thought it'd be quicker and more adaptable based off the alliance if we could do both. At our first competition, we only did the double because we didn't have enough driver practice, and it was our first competition competing, so we didn't know what would work and didn't work, and there weren't a lot other robots getting in our way too much, so we decided to go from the double. And then at the next two events, we decided to go through the single because we found it was faster and easier for both the drivers and human player to drop the cones in and pick up the cones, then come around, then lining up for the shoots or for the double stations. So yeah, that was our game strategy, and then we also and the reason we wanted to pick up from the ground is because soon we realized these four dots have game pieces on them, and we wanted to be able to pick those up and score them early on in the game. But to do that, we needed to have a robot that could pick up off the ground, which we did. So yeah, um, so here I'll sign it. Yeah. So yeah, as you can see, was the final CAD we had for the robot. We tried making it so the way we did it is we have all the different subsystems in different documents, and that allows us to be able to import them into one document and then change them as needed. The one drawback to this is if ever you make a small change to a subsystem, you have to re-upload the whole thing, but that's not bad. So yeah, so this was the CAD we made. There's a few things on here that we don't have, like electronics, especially the ones that are in the arm, and that was because we weren't sure how we were going to do those yet until we built the arm. We weren't sure if the motor controllers were going to be on the side here or in the arm, and we ended up putting them in the arm. As you can see, this panel here, that's what it's meant for. There's electronics in there. So I had this loaded, but the first thing we made in our in all of our like design process was the the arm, which when I originally pitched it to the rest of the team, I called the double pivot flippy doodle because uh it has two pivots and then it has a wrist to flip around the cone. So it has one pivot, two pivots here, and then a third pivot here that rotates, or the flippy doodle, which flips the cones around. And the reason we did this was because we wanted to be able to pick up from this side and then bring the arm over and score on the other. So that way we could just be faster at scoring. Um, we use the Julia feature script studio that's free on Onshape to make all the parts. So that's how we made the extrusions and the gussets. We made we made the superstructure as soon as we know our dimensions to our chassis. And so yeah, that's how we use that. We use it mainly, yeah, the Julia feature script for the making the extrusions and gussets, which is really useful. And we tried making them like universal so we could use them throughout the robot. We ended up only needing gussets for the superstructure, so it wasn't that bad. But yeah, that's how we made the superstructure. We only made half of it in the part studio, and then we brought it into the assembly and made it one full like thing. We added these X's for support. We only ended up putting these ones in because it was really hard to get the host line up for this. So and then the the cool thing we did for the gearbox or for the gearing for the arm is we made it like a 260-to-1 gear reduction overall. So the way we did that was we had an old tank drive set from West Coast Products, an old tank drive gearbox that was yeah, that had around a 10-to-1 gear reduction, and we slapped 3 motors onto there so that we could have the arm could be faster, and we could also have it be fast once we got the robot programmed and like cycles running. We could have the arm running faster and have more potential for scoring. And so after it went through the gearbox, it came out to this axle uh, had had pulleys that went up to taller pulleys, to from small pulleys to 10 pulleys. These are 14 pulleys, and these are 54 teeth pulleys. And then we had 12 teeth sprockets for 35 chain go to 64 teeth sprockets that were directly mounted onto the arm. We also decided to make this axle dead axle hole. That way we had less backlash on the arm, and also so that these two um like pieces of metal would be somewhat like stable instead of just floating. We made our own change tensioners as well, which was really cool and really simple. We went through 3 different versions of these. One of them was fully printed, 3D printed, and after a few minutes of use, those just broke immediately. Then we had plates. Only did CNC plates, which worked okay for most of the season. And then we ended up making these out of metal, which worked really well. So the way this works is you have two screws that go through the entire thing. You don't need a second one of these. You just need one, and then plates, and then a plate on the other side. But the way these work, these are bearings, and there's a washer in between the bearings and the plates on both sides, and then you just have a screw that goes across that you're able to move, and then you're able to move this up and down as the chain loosens or tightens if you remove a link, so that the chain is always tight and has low backlash. So this was how we made the first pivot and the superstructure. It's quite simple. Then we had the arm, which had the sprockets directly mounted to it. We used thick wall at first, and it worked really well. We later on tried switching to thin wall to lower the center of gravity of the robot, and also just to make the arm lighter so we can make it go faster. And these walls started the like holes that were here. The sprocket started like bending in, so we had to put in spacers inside the tube, which was kind of annoying to do, but we figured it out and it worked all right. And so yeah, so we had two because we wanted the system to be redundant, and also just so it wouldn't have not only one part of an axle would have a high um load, because we found out in our previous season that if only one part of an axle has a bunch of torque on it and a bunch of load, it will twist. And we found that out because we have an axle in our workshop now that is twisted, basically, and we call it the Twizzler because that's what it looks like. And so yeah, one thing we also did is this axle back here is a dead axle as well, and was meant for springs to go on it. So so we kind of had counter springing. It worked okay. We didn't make it as efficient since this was an afterthought and not like when we were designing it. We wanted counter springing. And yeah, one thing that we don't have catted in here that we ended up putting was along one of these walls we put a hex absolute encoder. That way we could track the position of the arm instead of through the pulleys, because after our first two competitions we realized that no matter how tight we had the belts and the chain, there was bound to be some skipping. So if we had an encoder on the arm itself, we would always know the exact position instead of just the what the motor thought was the right position. And it ended up working better, and yeah, and the arm was skipping less. So on the arm, we also had the motor mounted for the second pivot, and we had it mounted all the way in the back because we wanted the like there to be less force on the arm. The way we made this was we used the um max ultraplanetary gearboxes and had a 125 gear to 1 gear deduction on this, and we wanted that because we wanted to be able to flip the robot over if ever it stuck, and we knew this was just going to be for the in and out movement, but we didn't need to be fast, and we just wanted to play it safe with the load. Having that really high load also, or high torque, also allowed us to n- not need as much clearance, if that makes sense, I guess. And so yeah, we also added one of our custom chain tensioners on the side here that goes up and down. And the way this axle was, it was also a dead axle during the season, and we made a dead axle because we saw 2005. What they did is on one side they had cables, on the other they had a sprocket. So that's what we ended up doing, and it worked pretty well and was really nice for cable management because we had the arms come down and then through instead of having them come here and have a massive loop that would bungee back, and it just looked nicer and worked better than what we had. And then we this was our last pivot and also the wrist. So the way we we designed this to work two ways. One way had it so both the motor that spun the intake and the motor that rotated the intake were on this plate, and that's what we originally wanted to do for our second or third competition, but we realized that that was too complicated and we just ended up not doing it. We just had the one motor, so get rid of this, and this, and it was just like that with the intakes mounted direct onto here. Having this type of having the intake easily hot swappable was really nice, because if ever we wanted to try a new type of intake, or just put on like if it broke and we wanted to put on an intake that worked, we just took off. We had shaft collars here at the front and bottom. We just took off those shaft collars took the gear off, put the intake with the correct gearing on it, and it worked really nice. And yeah, so the way this worked, the the wrist doesn't require this axle to spin for it to be able to rotate the the wrist, which was really nice and part of the design. And we wanted that because we wanted the axle to spin bevel gears, which spun the intake, which we ended up not doing because it was too complicated for us and we didn't have enough time to test it and get it all that figured out. So yeah, so this is our second. So if I come back to here, it's all combined. The pivot one, which which we originally wanted to be a 4-bar actually, a virtual 4-bar with the second pivot, but we were like, oh, it's gonna be really hard to start in starting configuration and then also be able to score on the other side if we have it like that. So we ended up making 2 pivots. So yeah, so I'm gonna show y'all our first intake. This intake design was we took inspiration from Team Mechanical Advantage. Here I can show you their robot a little bit. Yeah. This is their intake. They released a CAD of it really early on into the build season, and 2 or 3 weeks before competition, our intake team still hadn't figured out a design. So we just found it and was like, okay, we're building this, and this is what we're gonna work with for our first competition, and ended up being what we used for our second competition as well. The way it worked is it's 2 3-inch wheels at the front, and then 2 or 4 4-inch wheels in the back, and these front wheels would grip the cubes basically, and these would grab these would these front wheels would grab the cubes, and then these back wheels would grip onto the cones. We tried coming up with this spaghetti type like roller because we thought it would increase our range of motions, because basically we just attached like the bits are just these have a hole in them. These would be 3D printed, and then we'd put either like surgical tubing or use tread in there or something that was compliant and had grip onto it, and then we put a screw to hold it on and put it on the axle, and then basically the idea was it would increase our range of motion to pick up, because this would spin uh, this would it might not be constrained correctly, but basically, yeah, okay. This would spin with a long teeth and come back in. We found out it didn't work well because um they were either too compliant or they popped the cube, or once the other hit it, it just pushed it away instead of bringing it in, or like the opposite side hit it and bring it in. So we just ended up removing them, didn't even bring them to competition. But yeah, this is how we mounted the hot swappable like intakes. It's just 3 holes for screws, or 6 holes. We ended up using I think 4 every time, and then yeah, so and then you'd have the bearing back, or the bearing in here with the axle that comes out and a shaft collar to hold it all together. Um, our idea was by the end of the season we would replace this motor here with bevel gears to make these spin, but we just ended up not having the time and not figuring out how to do this. But yeah, here I could show you a little bit more of Mechanical Advantage's intake. It worked really well, and we tried taking a lot of this team's strategy, like game strategies, when we had this intake. We later on switched it for an intake that resembled 2005 intake, and I'll show you all that later. But yeah, so the drop and the shoot we took from them, and yeah, as you can see there, yeah. This was how we did that attempt. Uh, it worked well. Yeah, so you can see the intake right there. And then score, and then we're gonna go. So yeah, as you can see, the robot was really tippy too, and we had to add ballast at the base to keep it. Yeah, and then We just had a human player drop it into our intake, and it worked really well. We ended up doing that instead of um, picking up from the shelf at our second competition because it was faster. And this side roller intake, worked really well, or it worked decently well. The only thing is, it, if cones were tipped over, it couldn't pick them up off the ground, and that's something we didn't like. So we ended up switching over to this intake, which prioritizes cones that are tipped on the ground and can pick up cubes. This was based off 3005 intake here. I could show y'all. This team, in my opinion, had one of the best robots this year. Uh, and so yeah, so you can see their intake is this part right here is meant for cones, and this part right here is meant for cubes. So we tried copying them. And we'll see. I think they pick up. They pick up. Uh, yeah, you can see there how they pick up cones that are sideways, like, and it's held into their intake like that, and they're able to score them. Really similar design to us, and so yeah, I don't know if you saw that, but that was just touch it and own it basically, and that's what we wanted to do. We weren't able to do it as well because it was a replica and we don't have as much experience as them. But yeah, so this was what the intake looks like. Uh, we designed our cube cage. So yeah, so the first thing I did when I designed this was figure out the cone geometry, because uh the cones have to be able to be stuck in here and be able to picked up from the tip or the base. And so the way I did that was this back here is smaller than the diameter of the front, and yeah, so it clamped on, and so if I grab the tip, it'd be stuck in like that, and so yeah, this design was simple in how it worked, but was really hard to execute, and I don't think we did a good job at executing it. Because so the way this works, so I'm sure as you can see, if you were to put the cube here, you wouldn't be able to. Uh, Up here, you wouldn't be able to. So we had to also create a cube cage. The cube cage worked really well. The cone gripper only worked okay. It only works where here you can see here. It was hard to precisely place it, but it only worked if we got onto the cones at a very specific angle. I don't know if you saw that. Yeah, look at that. Only got the cones. If we got it at any other angle than that, it wouldn't pick up the cones basically. And we didn't figure that out until we were at competition, and it was too late for us to switch. Um, in hindsight, we should not have put this intake on the robot. It was really good concept, really great designing from 2005, but we didn't get enough driver practice or prototyping time basically to get it working well. So we should have stayed away from this design. And then we also had another design which was like a claw that clamped on the sides, which we never actually put on the robot but had a prototype of, and it didn't work great. And yeah, coming back to here, this is a full robot CAD, and the way we did this was we first made the chassis, and then after we made the chassis, we made this piece which shows us how like the how high and how like out the robot is allowed to reach. And this was very useful. This was very useful for designing and making sure the robot fit in the constraints. Because one thing we didn't realize when we designed until we put everything in and tested it was if the intake is out and the robot's fully extended, I don't know if you see, but that's outside of the bounds of this box, and that's not allowed. So we had to make sure that whenever we went over, the intake would be in. And then also, having this box cage also helped us because our intake, when in starting configuration, starts like the robot starts like this. Um, but basically, the fact that this is curved made it illegal, so we had to make it straight, as you can see. So we have in here, it's a straight thing instead of being curved this way, which made it legal. Having this also allowed us to make sure this sprocket wasn't outside frame perimeter. And there was another thing this was useful for, which was um oh just like visualizing how legal the robot would be. Um and yeah, having this full so I don't know if y'all saw, but all our different like subsystems are in different like files altogether, which is fine and works well for us. I'm not a fan of it. Our mentor is the one that really pushed us to do this, but I'm not a fan of this because it means if ever you make a small change, like let's say I were to change this wheel and make it on the inside, I could do that in here, but it wouldn't update on here. So that's one downside, but it does make things load a lot faster. Because for example, on here, I'm pretty sure, yeah, we have the full field and that takes a while to load. And if we had to like just make a, as I said, just switch a wheel on the intake and that had to load as well, it would just take a while. So it has its downside. Having the wrist, like the way we made it, allowed us to just be able to test different types of intakes in the robot. Because like, look, I could just hide this and then slap on a prototype. So this is a CAD that Mechanical Advantage made. It was very heavy and bulky and big, and so we designed what you saw was on the robot. We designed this. And yeah, so having this wrist the way we made it though, we're able to just to have this gear be on a revolute so it can turn as needed. Uh, and the intakes are on there. But yeah, as you can see, we could just uh put on different intakes. This was the claw I was talking about. It opens and closed like that. We never ended up test putting it on the robot because we just found it was inefficient. Uh, we also came up with a so this was the EveryBot our EveryBot style intake, and we we thought about this for a good minute and then realized that with bumpers that wouldn't work and it would be really heavy and this wouldn't fit in like going over in any way, so we couldn't do it. So yeah, one big thing I liked about this too is so we ended up having a belly pan on this uh later on. So at first we had a bunch of different plates on the robot which we use that uses metal that we called the cheese grater, and it's basically just the cheese grater is a bunch of holes that work together. That or it's like a piece of metal that's 1/8 of an inch that has of uh, a bunch of holes in it, and yeah, so we switched it to belly pan later on because we found out that having those different panels, whenever we collided strongly into things, it would break. And so we had yeah. Now I'm gonna go through some of the things I liked and didn't like so much about this robot. One of the big things I liked was the fact that we had this belly pan at the beginning of the season. So the reason we have this belly pan was because originally we had a bunch of different like zones that we used this cheese grater type metal, which is just like a a sheet of metal that has a bunch of holes in it. And we had, I think it was four different, or yeah, 4 or 5 different zones. One for the front, one for the back, one for the middle, and two for the side, and one for each side. And we had that because we didn't have enough. We didn't have a sheet big enough to cover the entire bottom, and B, because we wanted the entire bottom to like have a bottom to it and not just be like a hole in the robot. So so we found out after our second competition that that would break if we fighted too hard with other robots or into the wall. And so we ended up switching to one big aluminum belly pan, and this worked a lot better. This also allowed us to have handles in the on the belly pan, which made the robot easier to carry and made it easier to mount stuff onto this because uh, if we wanted holes, we just catted them out and they'd be there for whenever for the thing we needed, and they'd be the exact dimensions instead of already pre-drilled holes that were like manufacturer made or holes that we like. Yeah, they were made for the parts that were in there, which was really nice. Another thing I liked about this robot was the modularity of the intakes, just being able to swap them on and off. However, that came with disadvantages. Having the wrist made wiring really annoying if because uh, the the intake could only rotate how so much before uh, before it broke. So yeah, and actually I'll probably show a match video later um in the video that talks a little bit about this, but we had to hard mount one of our the intake for our off-season events because the intake just broke and we didn't. It was really hard to fix, and we didn't want to fix it, so we had to hard mount it. And basically, instead, we used this side roller intake and hard mounted it. So you see how it's mounted to this axle. We just did that to second pivot instead of this. It was just mounted onto the gussets the way it's mounted around this. This robot was successful-ish. Whenever we needed it to perform well, it didn't, and whenever we needed it to perform okay, it performed really well, which was kind of sad. But that's just due to the fact that we didn't develop it fast enough. And whenever we tried changing something, we either did it too quickly in the sense that we didn't test it enough, or we just did a bad job at testing it. One thing I will say, this robot taught us a lot about wire managing, and we found this thing called CAN branching. And if you don't know what it is, so CAN has to go through every motor on your robot. And so the CAN branch is basically, so this CAN needs to be a loop, it has to be plugged into your PDP and all the way to your radio. And basically a CAN branch is we you put a resistor that basically kind of like ends a branch, but the way it works is you have a loop, and then using a 3-wire connector, you have like a part of it go off, like branch off, which is what it's called, a branch. And that branch, instead of putting it back in loop later on, what you do is you just put a resistor at the end, and it works really well. We had that for our entire arm, and it worked really well. Whenever our arm broke, our chassis wouldn't. Uh, after so this we didn't have this till our second competition. So if you'll watch some of our first competition matches, one of the wires will get loose for the arm, and we'll just be stuck there on the field. While at our second competition, there's some matches where the entire arm and intake don't work, and this chassis still works, and that's because of those um, canned branches, which was really nice. This robot was really big too, and that is something we should have thought of for this game, seeing as how you had to fit 3 robots in the charging station. So the way we countered that was there was no way to counter that. It was we should have just made a smaller robot. Um, we would have had to do some weird things with the superstructure to make it fit, but we should have either had these motors come up like the regular SDS, the regular configuration instead of the SDS, and we should have also maybe had pieces of extrusions that came uh, from here to here. Maybe I don't know, but we should have tried making it thinner, so it wasn't like an inconvenience. Uh, Having this arm flip over the robot though caused us to have a really low center of gravity and have it all in the front right here. So we ended up adding like gym weights. Our coach, or yeah, our team like coach mentor went to what is it, academy, and just bought like gym weights for us and just used that and as counterweights, which worked really well. And so now we just have like I think around 50 pounds of weights and that we could just put on a robot and like change the center of gravity, which works really nice because we took him off. We put them on while we were putting the arm on, and then we're like, we should test the robot without this. And the robot was way tippy, way more tippy, and was way harder to control, like if it would fall over or not. And then we put them back on, and we had no problems. We could go all around the field. And so yeah, this robot also lacks our electronic layout. We just kind of slapped it on there. It'd be I think we should have done a better job with this and actually planned out where the electronics were gonna go. Because A, they would look nicer, and B, it'd be a lot less of a hassle to figure out when there's a wiring issue. And yeah, uh, I this robot was fun to build and was a great starter. So actually, this robot we decided to keep it assembled for the season because we found we looked at previous games for FRC and realized that we just switch the intake depending on the game, and it can somewhat play the game and somewhat play any game. And so that's something that we wanted to keep for prototyping, having a robot that will basically always work if we just swap the intake. So that way, heading into the season, by week 2, we could already be doing driver practice or um, figuring out what's going to work on a robot and what isn't, which is really nice. And this robot is also like quite simple, so modifying it isn't hard. Because like, let's say we wanted to make this arm smaller, that's fine. And if we want to make this arm smaller and pick up from the ground, we just make um this extrusion smaller and this one bigger, and there you go. And there's a bunch of small changes. Another thing I'm not a fan of on this robot, there's a lot of dead space. Like for example, inside the superstructure on the sides here, there was a lot of dead space. But that's something we figured out use for over the season because at first we had nothing there. Then we put on weights because we thought that we were light enough to put weights and we weren't, so we had to take them off. And then we found out that for good wire management, like it has to be nice to look at. And so we set it up like we zip tied all the wires that went to the motors really nicely and made it look really nice. Because some one in a match during the season, when we slammed into the wall too hard one time, we had like a loose can wire dangling here, and it came into the swerve modules into the gears and ripped the wire. So we were dead for the rest of the match. So having neat wiring is something we learned that was very important for FRC robots. And yeah, so that was my explanation on why we made what we made. I'll also probably include a few videos of how the robot made or how the robot did. Here's one of our matches. Uh, we had we didn't this year for FRC for the 2023 season. We didn't prioritize ranking points, which was a big problem. Because, like for example, the chart station, if you were able to balance on it in autonomous, you could most likely get the ranking point for that. And we didn't think about that until we weren't. It was too late for us to worry about that. And so yeah, and because like the Lynx is really hard, you have to have 2 or 3 really good robots to do that. And while the charge station, you just need a robot that can balance. And so yes, this was a robot. Our robot was really big and heavy, so as you'll see, we clashed with the other robots, and it just wouldn't care. Our robot just wouldn't care. So here, there's a big clash coming here. This clash right here, actually, so since our robot was so heavy, this clash right there that happened between Kryptonite and us broke their intake, and it took them the rest of the day to figure out what happened and how to fix it. And yeah, and this also, you can see the superstructure is dangling around. That's when we realized the panels. This match make us realize that the panels, the different size panels, just wasn't gonna work, and we had to have one valid plan because the superstructure was just loose and like held in place and not actually like put in. So yeah, this year was a okay season. We're heading into the 2024 season now, as you can see, and I hope to make it an even better year, an even better robot. And yeah, thank you for watching.